Okay, so yeah, let me just get going. I will have to run very quickly after the end of the talk because of the travel situation. So I'm going to talk about a flow. This was motivated by work of Luo and Hou, but actually the problem dates back earlier to work by Steve Childress. And in fact, a lot of the ideas of what I'm going to discuss are contained in Steve Childress' papers. So just to tell everybody what the flow is, it's flow in a cylinder, so it's wall bounded, it's axially periodic, it's Euler flow. The initial condition is pure swirl, so you have a sinusoidal azimuthal velocity, counterclockwise in the top and clockwise in the bottom, zero at the midplane, zero at the midplane. The relevant thing we're going to look at initially, at least, is the vorticity, which is the axial shear of the swirl velocity. Okay, at the midplane, in fact, at the cylinder wall at the midplane. Okay, Luo and Hou did a very high resolution simulation of this flow, and they found evidence for a finite time singularity. And this was referred to a couple of times last week. So here's a plot, the log of the vorticity, that vorticity vector, which I showed there, as a function of time, and it shows an extremely rapid. And then they did a lot of other analysis I don't want to get into. And just note the divergence, the exponent is about 2.46. Okay. So that's the flow I want to look at it. And the thing is, I want to look at it from the point of view of somebody like myself who does continuum mechanics and thinks a lot about mechanics. And I want to think particularly about what it is about this flow that potentially leads us to a singularity. And I'm not trying to solve the general problem. I'm just trying to understand this particular flow. I want to be clear about that from the beginning. And the thing is, if you think about this problem, it's very natural to focus on pressure rather than other things, because if an inviscid flow is the only stress acting in an inviscid flow, it's the only way you can accelerate the flow. So it's a natural thing to think about when you do mechanics. So, and Luo and Hou had exactly one visualization of the pressure in this paper, and this is in fact partly how I got involved in this. So you're looking at a meridianal slice through the cylinder, where the place where the singularity is going to form is on the outer wall of the midplane, which in this figure appears down here. And this is the pressure field that they saw, and this is as close to the singularity time as they can resolve. Right? This is as close to the singularity time as they can resolve. And it didn't take me any time at all. You look at these contours, and you can be sure that there's no possible way that this flow could be singular. This is not possible. If you have pressure contours that look like this flow cannot be singular. So for about 10 minutes or so, I was convinced they had made a serious error. That's just not possible. Now I was wrong, they were right. But the story is interesting. So I'll let you think about how I can be so sure so quickly that couldn't be singular. So what I'm going to do is I'm going to first describe the flow in more detail. I haven't really described it in great deal. I'm going to remind there's a broad audience a little bit about Euler singularity, the aspects of it that I need. Then I'm going to discuss the mechanics. Then I'm going to discuss how you can use that well, I'm going to decompose the pressure and slide a lot under the rug there, and then discuss how you can model this with the closure. Okay, so the one bit of physics that I really need you to know is that curving a streamline costs you a pressure gradient. Okay, and everybody I think knows that you have a swirling flow and you have high pressure on the outside and low pressure on the inside. You have to have that. A curved streamline is an acceleration. You have to have a pressure gradient. It's the only stress we have in this flow. It's the only way we could add a force to the flow. It has to be a pressure gradient. Okay, and then you need to know that it goes as a velocity squared. That's going to come up constantly in this talk. It goes as the azimuthal velocity squared. Right. So, and people know this teacup effect. So this is Lorette stirring some grains in a dish, and contrary to what you might expect, they're slightly denser than the fluid. You might think they could go out. In fact, they go like it's the teacup effect. I think people are generally familiar with it. You can do anything at the institute afterwards if you're interested. The thing is, Einstein is credited with the first person to explain it, although people before Einstein surely couldn't explain it if had been asked. The reason it occurs in a teacup, if you have a bottom boundaries, there's a viscous boundary layer there which slows down the azimuthal velocity. The azimuthal velocity goes to zero, and hence this balance between the azimuthal velocity and the pressure gradient is no longer satisfied. You have a pressure driving flow along the bottom wall, and then you get recirculation. It's secondary flow. And we refer to that as the secondary flow. So this primary, I didn't indicate, this I'm going to call primary flow, the swirl, and that's the way it works. Okay, this a similar thing, you can do a similar thing in this case. You replace the bottom boundary layer by just with symmetry. Okay, so you have swirl on one side of the top and the other side of the bottom, zero swirl to the center. By symmetry, that will remain zero swirl. So you have exactly the same situation, but without a bottom. Okay, and so what you're going to have is you're going to have swirling flow here, that will give you a high pressure, swirling flow there, that will also give you a high pressure. Notice it doesn't depend on the sign because it's quadratic. Keep repeating that. Low pressure in the center where there is no swirl, so you have a pressure gradient acting. So this is the way you would explain it in terms of pressure. There's an equivalent explanation in terms of vorticity. I can explain in terms of pressure. That will drive a secondary flow, which for the full period of the cylinder repeats this 4 times. Okay. The teacup is just 1/4 of the cylinder from here to there. That would be the teacup that is repeated by symmetry. Okay, I got it. So that's the secondary flow. That secondary flow, you can see, is going to drive axial velocity towards the midplane. And when that happens, what's going to happen is it's going to bring the swirl with it. You're going to drive the swirl towards the midplane, and you're going to intensify the vorticity. Okay, and that's the mechanism. That's the basic kinematics of what happens. Okay, I made a little model out of things I managed to pull around from the institute. Okay, so here's your flow. Okay, and if you just had straight flow here, it wouldn't do anything, right? It's oil, there's no viscous stresses. Okay, but if you put this in a container, so it's being forced to be curved. As soon as you do that, you introduce pressure in the radial direction, which then necessitates pressure in the axial direction, and it drives these together. I even brought little bonus factors. Now, so never mind this. All right. Anyway, so that's your vorticity blow. Okay, it's this gradient of this swirl velocity that is the vorticity that's blowing up. Kind of key that you understand that. Right? Okay, good. Any questions? So now I'm going to show you a little movie from my simulations. It's the same thing. You see.
Actually, I do have a question. That's okay.
Yeah, let me just okay. So you see the movie that's out of the plane into the plane. They're coming together. Okay, guys, go ahead.
In the previous slide, the secondary flow that you've described, if I'm understanding the coffee cup analogy, it would seem to be driving the particles away from the center.
Well, it depends on, so it's here, and then it drives the part, in terms of the teacup, it drives the flow along the bottom of the teacup towards the center, and the tea leaves are more dense than the fluid, so they settle in the bottom center of the teacup. If you're asking about the teacup.
Oh, in that movie, the things were settled on the bottom.
They settle on the bottom.
I understand.
They're more dense. That's key. So watch this movie twice more. Now what you're seeing is this. Okay. And that gradient of velocity, that's low. This then is as close. This is what that looks like. As close to the singularity time as I can simulate this kind of basic simulations. This is what the secondary flow actually looks like, not just a sketch, but the actual secondary flow looks like this, and this is the driving of the flow towards the midpoint. And let me just say, this is the meridional flow. This is most of what we're going to see are these meridional planes. So theta equal constant, and it is axisymmetric. So obviously, you're in the middle of the plane, and you're only looking very near the outer walls. What I'm going to focus on then is there's an enlargement here of a very small region, 10 size 10 to the minus 3. This is an enlargement, and this is what I care about. So this is a pressure field and the meridional velocity in the plane. You don't see the swirl. Okay, and it's this pressure field that I want to understand. Okay, in particular, I'd like to know what it is about this pressure field that gives rise to this interval. What it is about this that gives rise to this. Right, so let me give you a, I know that there's different expertise in this audience that we can discuss this equation, and there's some things I'm going to emphasize in. So I'm going to consider inviscid Berger's equation, our friend, it's been mentioned many times last week. We know that if I'm going to start, always consider an odd solution. You evolve it, you get a singularity. It's normal to think of that in terms of the characteristic equation. I want you to think about this in terms of inertia. That's the word I'm going to use. As we know, this is a statement of the acceleration of the fluid. And over here go the stresses. There are no stresses in inviscid Berger's equation. It's only, so the acceleration is equal to 0. So you invoke Newton's first law. Velocity is equal to a constant unless acted on by a force, and that's why you see straight characteristics. That's a statement of Newton's first law. And I want you to think of it as inertia. So the fluid is coming in, there's no stresses to stop it. All the fluid particles move in straight lines, and they just overtake one. So it's that physical equation. Then the other thing for people who aren't familiar, the way I'm going to analyze this for the actual Euler equation, so that we do the first practice problem for the inviscid Euler, is I'm going to take a gradient at this point of symmetry, of odd symmetry here, where the velocity is 0, and I'm going to take the axial, the gradient of that. Okay, and we'll call that capital W. And throughout this entire talk, capital W will never mean anything else other than a gradient of the velocity. Okay, at this point. All right. So then you can work out what you just differentiate this in Berger's equation, use the fact that the velocity is 0 there, and you get this equation for the velocity gradient, which you can easily integrate up when you see the singularity. So you see the velocity, so you see the singularity just in terms of the velocity gradient at that point. Again, that's a standard thing. But it's very useful for me to show you that first before we. Okay, so if you haven't picked up on this yet, so I was using this, and I specifically called that Z with the idea of being analogous to what happens on the cylinder, where I'm going to be looking at what happens on the wall of the cylinder, and Z at Z equals 0 will correspond to this. That's the analogy that I said. Okay, now the difference is here for Euler, we have the full 3D Euler, and we have the pressure stress. We have the stress on the side, so we don't have to understand. But the approach is going to be similar. Good. Okay, so again, I'm now going to discuss the mechanics of this, and to be clear, what I'm just going to repeat this over and over and over again, the same statement, but as we get further and further into the details, what I want to understand is what this pressure, how this pressure field, it's a real pressure field, this is real incompressible flow, nevertheless allows for a singularity. And I'll notice for you that that there's the inertia coming in, which we saw from Berger's, that's still there. This fluid has inertia is coming in, but there's a pressure maximum here. There has to be a pressure maximum in fluid dynamics. I could have told you that right at the beginning. You have to be diverting flow, the inward flow towards this midplane. I told you if you curve a streamline, that costs you a pressure gradient. You can't do that any other way than the pressure gradient. There has to be a pressure maximum at this point. There's no other way to this flow.
Yes.
Yeah.
With that picture, it's more or less exact the picture that I'm in 2D for the growth of vorticity. It's this result of Sverak and
would be very okay, gotcha.
Yeah. So what I'm saying is that something like this does give to double exponential growth, but may not give rise to singularity.
We'll discuss that. It would be very interested to know how this what this approach might have to say about that example. I think that's a very interesting question. I'm wondering if I could about, but I don't know how to approach it. This is 3D then.
Yeah, of course.
This is crucial. I mean, I lost my little yellow vectors didn't stick on. But this is it's a 3D flow. That's a good one. Okay, so I have to account for why that pressure stress isn't sufficient to decelerate the flow. And that's what I'm going to do. Okay. So I'm just going to write down the velocity gradient for Euler equation. If many people have done this or seen this, but I'm going to go through it. So I'm only going to evaluate, and I didn't say at the critical ring, that's where the singularity is going. Okay, I'm only going to evaluate the velocity gradient there, and there are only three surviving entries. W, as I said, is the axial gradient of the axial flow. That's all it ever means. B is the radial gradient of the radial flow, and omega is the axial gradient of the azimuthal flow. That's this gradient that I keep referring to. That's vorticity. But that's all that survives. And of course, this is a traceless matrix by incompressibility, so there's only two independent parts. Then the good part is that I look at the pressure Hessian. So I have the two diagonal elements. This is all that survives. The second radial derivative and the second axial pressure Hessian. Okay. And I'm going to refer to these as pressure curvatures, and I want you to think about it that way. If I take my pressure field and draw it as a graph, then these are the principal curvatures of that surface at the critical point. Right? It's very useful to have that terminology to think about.
What was W?
W is the axial gradient of the axial velocity. Okay, so that leaves me with these three equations. So if I just plug into Euler and evaluate the velocity gradients at the critical point, I get three equations and four unknowns. And these have a very clear physical meaning. This is an axial momentum balance. This is the same thing I had with Berger's, but now I have the stress that appears on the inside. This is vortex stretching. Nothing else to say about that. And then I have, you can do this one of two ways. It's either the pressure Poisson equation, which evaluates the critical rate, or equivalently, it's a statement about mean curvature. That the two pressure curvatures are equal to twice the mean, the sum of the two pressure curvatures is twice the mean curvature. So minus W squared is the mean curvature. That's a very useful thing too. So I have three equations and four unknowns. Obviously, I have to solve this. But these equations are very, very useful for understanding what's on. Okay. So I'm going to do three problems. And then there's going to be a quiz later because I'm going to come back to these same three problems. Okay, so pay attention. So the first thing I'm going to do is I'm going to scratch off the pressure. Okay, so that's going to take me back to Berger, obviously, together with the convection and I just passive scalar along with it. So I just have Berger again. I just reproduce Berger's equation, which we've already done that problem. It's a singularity. The vorticity now carries with the blow up of the vorticity with the same as. So, but it's just nice to know that it contains Berger's especially. The next practice problem is, let's suppose we have a symmetric pressure field. There's no reason you'd have a symmetric pressure field, but let's just suppose we did one. Then the pressure curvatures are equal. Okay, so I have my pressure question to worry about here. And I have, well, if they're equal, they're both equal to the mean curvature. Okay, so PZZ is equal to the mean curvature, which exactly compensates that. And if you look at the equations, I have my axial momentum balance is my nonlinearity is exactly balanced by my pressure stress. They exactly balance. Okay, W dot is zero and there's no singularity. Good thing. Okay, it's a two-dimensional flow. It couldn't possibly be singular. All right, so if I have the symmetric pressure, and my view is that that is probably the simplest example that you would ever show to somebody if you want to just take a saddle plane and do this and to show how the pressure stress exactly balances nonlinearity to suppress what would be a singularity in Euler. It's suppressed when you do pressure. That's the example I use. All right. Oh, and that's the thing. So I have, again, I'd like to think of it as I have a curvature budget to use. And if I use them equally here and there, and I have a pressure gradient here and a pressure gradient there, I've used them equally, and that will exactly balance the equilibrium. So W dot will in fact be exactly zero. Okay. And now let's do. Now let's just do the real problem. So the real problem is it looks like this. The pressure field looks like this. You maybe didn't really notice very carefully what it looked like, but now I'm showing it to you. Okay, these pressure curvatures are not equal. The radial pressure curvature is larger than the axial pressure curvature. They're not equal. Okay, so just I will state them as define A such that this is true, and then I define with A squared so that I get this is a ratio of length scales rather than just this. Okay. There. Okay, so and you can see that in this figure anyway, the A is bigger than 1. Okay, that's very important. But let's just play with some algebra. You can just, whether or not A is bigger than 1, you can just do some algebra, and you'll get that, of course, that if these two aren't equal anymore, you wouldn't expect that this to exactly balance that, and it doesn't. I mean, you get a statement here, depending on the value of A. And you can see if A is bigger than 1, this will be less than 1, and this won't exactly translate. And so if you allow me to, I'll just redefine things. I have W dot and omega dot and written in terms of gamma. And if you just allow me to, for the moment, to assume that's constant, I can integrate these up and I get a singularity. Okay. And this, I get a blow up. So the velocity gradient will always blow up with exponent minus 1. That will always happen. But now the vorticity blows up with exponent minus gamma, which is why I define it this way. Okay. So we have this blow up. And if you look, I told you, if you look at Luo and Hou simulation, the exponent was 2.46. If you translate that exponent back into the A is 1.54. Here I've shown 1 to 1.54, as close as I could do it in Keynote. And you see that that is clearly the signal of that exponent. That is what you would expect to see in a pressure signal for blowing up by this mechanism with that exponent. And there it is. It's really the thing. Okay. I'll get back to the none that I'm assuming constants. Okay, so what I'm saying now is that once you make these unequal, then you have your pressure, but you have your curvature budget. You use bunch here and less there, and you don't have enough to suppress this incoming inertia, and you'll get blown. And that's a very simple problem.
What makes you think that A should be time independent?
But let me get, I'm gonna, a lot of the time, address what happens there. So you can now maybe appreciate why I was confused by this. This is wrong, this contour is going the wrong way around. The thing is that you hadn't plotted on with the right aspect. You plot the right aspect rate. Now you see that's the signature you're looking for a blow, not the other way around. You need that signature. You need this to be bigger than that, so that you have less pressure gradient in the axial direction. So that's why I was confused by it. But there it is. As close to the singularity time as they could measure, there's that signal. That's what you should be looking for. That's the signal for blow.
So the curvature of the radial is less than the
Greater.
curvature of the vertical.
Now the curvature of the radial is greater. So you're throwing fluid inwards faster than you're decelerating coming.
Greater, so greater pressure.
Yeah, so you're throwing fluid radially inward faster than you're slowing it down axially. And that will be nice. So these are simple calculations. Okay, so the thing is, and this gets back to the non-constancy. So as long as this is persistent, as long as it's persistent up to this time, this will be the same. I don't do theorems. I'm sure that half the people in this room will turn that into a theorem. It doesn't prove anything, but because you need these are the theorem to be satisfied. But it wouldn't be difficult to say that to write this formula down with the conditions. Right? It's just too simple. Okay, so now this is what I really have. So that's the introduction. So this is the easy part. Okay, if you have this pressure mismatch, then you don't have enough stress to decelerate the incoming fluid. And then the question is, why does that happen? Okay, so now I'm going to explain it. So again, the same question. I got somewhere in it, but I still haven't told you why. So now I have to do this. And for this it gets to the, there's a lot of, applied math technicalities here that are not very important, and I don't want to really get involved in communicating. You can read the paper, but I'll try and give you the highlights. Okay. So this part is known, this part is easy. We have the Euler equations together with its boundary conditions. All bounded flows, so the penetration is 0. At the radial velocity at the wall, later on, I'm just going to call this wall, right? But the radial velocity at the wall is 0, okay? So, you go back to maintain incompressibility, the pressure must solve a Poisson equation together with the boundary conditions such as to maintain fluid. So fluid is doing 2 things, and the pressure field is doing 2 things. All right, so this is what we have. We have our pressure Poisson equation together with this boundary. Now, something that I think is very, very underappreciated in certain communities. This is a linear equation indeed. I know, but it's somehow forgotten because it's not linear in the velocity. It's nevertheless linear in pressure. So we can exploit that, and we can separate it just as you always would. And I'm going to separate it first into contributions through the original velocity and the swirl. I'm going to do those separately. You can separate those 2 contributions to the pressure field. And then I want to separate the parts from the swirl having to do with incompressibility and not maintaining the flow. You can separate all those terms out separately. Okay, and then so this is where the details are that I don't really want to. I'm going to sleep under the body most of the pictures, and I hope that will suffice. I'm sure you could all write this down if you. So let me just show you. First, I'm going to just separate the pressure into 2 parts, one due to the marginal flow and one due to the swirl, and I will explain it in pictures. So this is the pressure field, the full pressure field, and it's a linear superposition. There's no approximations. This is just a linear superposition of 2. One, I'll call it P2D, and it's a function of the pressure field. These are the pressure contours that you see here. It's determined by the radial and axial velocity. So the velocity field in the plane, all right? The velocity field is shown by these streamlines here. It's global. It's the whole cylinder. I'm showing you this piece right here. This supports all the curvature, mean curvature of this flow. It has to all be contained in the original field because it's dependent on the original field. It can't be dependent on the swirl. So this and this have the same mean curvature. So that's one of the 2 pressure fields. The other one is dependent only on the swirl. So the flow into and out of the plane. And that generates this pressure field, and this pressure field necessarily has zero, necessarily. Zero curvature at this point. Okay, so it's a saddle point, and it encapsulates the teacup effect. High pressure here, high pressure here. It's this there's an axial gradient of the swirl, which you don't see. So I'm showing you this one, but it gives rise to so towards the midplane and away. It's entirely contained in this pressure field. Okay, so I've done that. Now what I need to do is I need to separate this swirl pressure contains both the boundary, contains both the boundary part and the interior. I have to separate boundary from interior. And I don't know if any of you have ever done this in cylindrical coordinates, but if you do it in cylindrical coordinates, you'll realize if you try and separate a Poisson problem, the boundary and the interior, it doesn't work that way. There's a third part that you have to do to separate. Okay, I'll just talk to the experts. If you were doing a Poisson-esque approximation, Poisson-esque, this wouldn't occur. So I'm just going to sweep it under the rug. I'm going to combine this with that. I'm not really doing anything fundamental. Let's just do this. Let's just do this. But I have two. I'm going to decompose my swirl into two parts. One part that is determined only by the swirl on the wall. It's not the interior problem. The other that is determined by the swirl in the interior. So I separate the swirl, the boundary from the interior. That's a standard thing to do in solving Poisson problems. Okay. Now let's look at this, at least near this place. So this, again, this pressure field that you see here is determined only by the swirl on the wall. Okay. It's a harmonic function. I heard at least 2 times last week people said under their breath, plus a harmonic function that we don't worry about. And I granted in infinite problems, maybe you don't have to worry about harmonic functions, but this is wall boundary. This is a harmonic function. It's not doing anything towards the incompressibility of the flow. It's not, but it is a stress. It is accelerating the flow. It's just not accelerating in any way that controls for incompressibility, but it is nevertheless accelerating. It's a harmonic function. Okay, and this is the flow that the pressure field is generated by the swirl everywhere else in the cylinder. It is quite large if you get far, far, far away from where the singularity forms, but here near where the singularity forms, it's really comparatively weak. If you look at the axial gradient, it's even weaker. There's very little, there's some, and I will have to worry about this at the end, but for right now, I'm not going to worry about this. This is the key one right here. You see that the pressure from the swirl is almost identical to the component determined by the wall, the swirl on the wall only. Right. I think we can skip that. So here's the summary and pictures of this part, okay? So I have this mismatch of pressure curvatures. I can decompose that into 2 main contributions. One due to the in-plane flow, and that gives me this pressure maximum, which supports all the curvature of that. It's a almost symmetric pressure maximum. Not exactly, I'll have to worry about that later too. And this part, which is determined only from the swirl on the wall. And it gives me a favorable pressure gradient, accelerating fluid towards this. And this is the essence of the decompose. Okay. Okay. So then this brings, so are we okay before I go on? Is that good? All right. So this brings me to closure and the Hilbert transform. So here's all this up last week. So there's a rich history of this. People in this room will know this much better than I. I believe the earliest paper of this Constantine Maxim Minor from 1985. So I'll have a nice review of the many different models that people use to study primarily vorticity equations with transform. So these are the Euler equations on the cylinder wall. The exact. There's no approximation. Where you're going to have to get used to these variables. Omega here is, well, it's the vorticity, the azimuthal component of the vorticity on the cylinder wall. Theta is the swirl squared on the cylinder wall. I'm just going to refer to the theta as the swirl, but you understand it's the square of it on the cylinder wall, and U is the axial velocity on the cylinder. So that's my swirl, and that's my axial velocity. And there's also vorticity. Okay, so those are the exact equations, but they're not closed because they involve 3 quantities in their own. So Luo and Hou closed this system with this approximation, which you can justify. I think I can give a slightly better justification than they gave, but nevertheless, I agree with it. In fact, let me just say, I think it's a great close. I think it's a great model. In many ways better than the model I'm going to break down. But in some ways, I think the model I'm going to break down has some advantages. But anyway, you close it this way now, the closest, and then we can simulate and we can understand information. And they get, and I believe it's proven, I believe it's now been proven that this model with this closure has a finite time sequence. I believe that's now. Okay. But let me just point out that's an approximation. It's a good approximation. It's a reasonable approximation, but it is obviously if it weren't an approximation, it was proof of singularity. Okay. So now this I'm doing inviscid. So the question then arises, there's a third variable here. So these two are connected to the Hilbert transform. Here's the third variable. What's the Hilbert transform of that variable? But you could just ask that question. You could have never done anything that I just talked about for the last 45, 35 minutes. You just ask yourself, well, what is the Hilbert transform of that variable? I'll tell you what it is. It's the gradient, the axial gradient of this pressure determined by the swirl on the wall. Okay. That is a unique physical statement about what that Hilbert transform of that gradient is. And what's fun about this is that's not an approximation. That's an exact statement. Right. So this is an exact statement, at least if you allow me to do so. Okay, so I have an exact relationship between these things. And if you just want to see the calculation, is h of theta is theta is the velocity squared, the swirl squared on the wall. Well, the boundary condition is that has to be equal to the radial pressure gradient on the wall. And a Hilbert transform maps a radial, a normal derivative to a tangential derivative in a sense. So that is what that is. Okay, so I have now a way of closing that up that I have an exact statement. Obviously, I'm not going to have an exact closure. But I have a partial, I have a different route closing the problem. Oh, I just say. Are we okay? Well, yeah, let me just give my second. So, and again, so it's this pressure gradient, this pressure field that I told you is so important, is determined only by the swirl on the wall, which is a variable in the equation. So I know, and I know it exactly. And so I know what this gradient is. So I know what's driving the flow, and I know it exactly. All right, so here's the thing now. I'm going to do this in primitive variables. So I have, these are the Euler equations now written in primitive variables on the cylinder wall. Again, they're exact. There's no approximation yet. So I have, I've decomposed the pressure gradient into three parts. The part depending on the original velocity, the part depending on the swirl on the wall, and the part depending on the swirl in the interior. Okay. So the part depending on the swirl on the wall is the favorable part, and I know that exactly, so I don't have to approximate that. The other two pressure gradients are adverse pressure gradients. This is the main one. This is a big pressure maximum here in approximate this. And this is this other little annoying one sticking. Okay? But I have to deal with this. Okay. So what I'm going to do is I'm going to combine them together and I'm going to model that. I'm going to put them together to one, which will be my total adverse pressure gradient. And this is where the single modeling assumption is coming from. Okay. Put this aside for a minute and just look at this. Suppose I had an exactly radially symmetric pressure field. Suppose I had that. Okay, determined by this original velocity. Then I could evaluate that pressure. I could evaluate my pressure Poisson equation on any ray going out from here. They were all equivalent because it's axisymmetric. Because it's radially symmetric. So if I go along this ray, I can evaluate that, and I integrate that pressure Poisson equation up, and I get this equation. So what this does is it tells me, well, I have an exact relationship between that pressure gradient and the original flow on the cylinder. Okay, so this is the approximation that I'm going to make. I'm going to replace these two pressure gradients with this pressure gradient given by this variable. Okay. So let's just see if it's any good. So here are the three. So I have this pressure field and this combined pressure field. This is what appears on the right-hand side of the Euler equations. Okay, this one I know exactly here. I don't have to worry about it. I know it exactly. This here, these are the two adverse pressure gradients. When combined, they generate this red curve here. Okay, at the pressure maximum, that's trying to decelerate flow that's coming in. I'm going to approximate this with this, and this is a blue, okay? And here I've gotten lucky. The God smiled on this problem. Because the blue curve is under the red curve, I'm safe. It's not a proof, but it's the physics argument is you're safe. What it means is I've replaced the pressure gradient associated with the red with the pressure gradient associated with the blue. The blue is steeper than the red. So I've taken this pressure gradient and replaced it with something that is even stronger, an adverse pressure gradient, and I've replaced it with something that's even stronger. It's going to decelerate the flow even further. Okay, so that should be safe, should be, okay. Okay, so then finally, this is the model I have. So I have, again, it's Euler equations written on the cylinder wall with this approximation, okay? So if you look at, so there are two variables, the axial velocity and the swirl. And two pressures, a pressure associated with the original velocity, and it's given in terms of the axial velocity. So I have a relationship between this axial velocity and that pressure. It's an adverse pressure, And then I have the swirl, and I have a relationship between this pressure with a favorable pressure gradient and the swirl, and that's the one that is exact. So it's a closed system. And this is my modeling assumption. Okay, let's look at the solution. So this is my equation. And remember, I told you the three cases and I told you to remember them. So now I'm going to do them again, but now in terms of this equation. Before I went to them at the critical ring, and now I'm going to look at them in terms of the model. Okay, so you're going to see three different cases here, Z and then fields as a function of time, and for different times, and then you're going to see, all right, let me just show you. If you're looking for blow up, the blow up will go W, that is to say the gradient of the axial velocity here is red. This gradient here is W, and that will blow up with this exponent. And the blue will give me the blow up of the vorticity, and that will blow up with exponent gamma, which will depend on the case. I'm plotting here the corresponding compensated velocity gradient and vorticity. Compensated in such a way that I should get linear dependence to zero at the blow up time. So reaching zero here corresponds to a blow up. Okay, so now I'm going to do the three cases. So I see the contained in, and this is why the advantage I think it has over Luo and Hou is that I can do the following. I can set both of these pressures to zero, and then I arrive back at my Berger equation together with this induction of a passive scale, which I can then simulate. And to no surprise, there's the odd velocity, here's the vorticity, and as the steepening of the gradient brings with it a steepening of the swirl velocity and the corresponding blow up of vorticity. And that's what you see here, the standard Berger's blow up together with the blow up of its vorticity. Okay. Now I can put in just this term. This is the 2D pressure, the pressure term just by the original flow. And if I put that in, I'll leave this one zero, and it's this case here. And in this case, I told you that that corresponds to the exact asymmetric situation. There is no gradient blow up. The gradient remains exactly fixed here. So there is no blow up, and that's the 2D case. So we have 2D flow. There's no blow up. We know that. Okay, then the final one is. So let's do the full model. So now I have the original pressure and the pressure due to the swirl. Again, just repeat from the last time. I know this one exactly. Okay, so there it's there. Then I do the simulation, and you can see I get it. Okay. What is happening is once I include this term, if I don't include this, then the axial velocity is not coupled to the swirl. All right. The swirl only acts as a passive scalar in either of these two cases. But as soon as I include this term, I get a favorable pressure gradient generated by the swirl itself. And that's the important thing as to why you might expect that is these things. I mean, this model is showing it, it remains to be proven, but the physics model, so as these come together. See, when you bend these things, the amount that they're bent and the amount of circulation is fixed. You're simply moving them closer together. So there's a certain pressure associated with this, which you're dragging with the fluid. So the pressure gradients are blowing up as well. Anyway, so it does, sure enough, it blows up. It blows up with an exponent 2.31, which is respectively close to the 2.46 full order simulations. So that's my claim as to what's happened, is that is that this pressure term, which is coupled, it's the pressure, it's the swirl at the wall. It's the swirl at the wall, it's strictly a boundary effect. The swirl at the wall is providing this favorable pressure gradient, which is driving the flow. And so, I mean, it's been discussed a lot how much this particular example is driven by the wall. It's very, very, very much driven by the wall. I originally thought that by understanding how this worked, I might see a way to pull it off the wall. That's not going to happen because it's happening because of the swirl along the wall. It's happening because of the boundary condition. So you're not going to pull it off the wall. Okay, so let me go to the conclusions then. All right, so this is what I claim is, in words, it's the mechanism. So you're generating pressure stresses are generated by the swirl along the wall. You have an axial variation of swirl along the wall. I think you got my picture of it. That variation of swirl along the wall generates a pressure stress. That pressure stress pushes these two together. That's exactly what it does. Okay, and it's such that as swirl is affected towards the critical ring by the axial velocity, it generates an increasingly large favorable pressure gradient such that the total pressure is insufficient to decelerate. That's the mechanism that doesn't exist in 2D. And as far as I don't know how to get it in 3D other than putting a wall in. That mechanism exists in this case because of the wall. Okay, anyway, so the velocity gradients blow up this. And then the other thing is that by this analysis, by writing down the Euler equations on the cylinder wall, I have a model of that, which is involves only one assumption. I've reduced it to one, which is supported by the numerics. I've replaced the adverse pressure gradients, which I don't know how to compute, with something that I do know how to compute, but it does seem to be safe. At least from a physicist argument, it's safe in that if these equations blow up the Euler object, that's not proved. It's just the physicist argument. And then what I like about it is it's a natural generalization of Berger's to include both pressure and vorticity. The thing is, vorticity enters this equation, and the gradient of this is vorticity. And we know you have to have vorticity to have a blow up, so it's nice that you include both in one system. And that's where you see the blow up, and it's published. That all makes sense.
Yeah, Dwight, can I ask about the physical situation?
Yeah.
So this is an initial condition flow. The boundaries just say no penetration, please. Otherwise, yeah. Otherwise, the swirl is what it is. Set up at the wall. You don't care what it is. You set up initially, and then you just let it evolve.
That's right. Well, that's it's certainly not driven in any other way. It's just an
It can't be, can it?
Can be what?
Can't be driven by the wall.
Oh, it can't be. Oh, you can't do work on the flow.
Yeah.
That's right.
You made a comment at one point that it's the boundary condition that's crucial. And I just want to sort of understand that. This is the curvature of the wall that forces the flow to be curved. Yeah, that's all you're appealing to.
That's all I'm appealing to. Exactly. That's all I'm appealing to.
Right.
And associated with that then is it because the swirl varies axially, the pressure field varies axially. It must. You could make the same argument for just I just think that in this case it's nicer.
Yeah.
And again, that's the pressure field associated with that confinement. And it has an axial gradient, which is driving the fluid towards. And let me just say, in case I don't know if you were going with this, but if you think about it, what's going to happen is mechanically, you cannot do work on the fluid. But the stresses are becoming, if you worked, I mean, if it made sense to build it a cylinder containing the stresses on the wall, the stress gradient on the wall is also blowing up. So there's the material that would have to hold this will eventually shatter because the stress gradient of the material is blowing up just as it does the stress gradient in the fluid blows up. Oh yeah, let me just say that. And then you see, I mean, that gradient there is that gradient that's the force that's holding the fluid in. And that's because pressure is global, if you try and hold it, you have to have a gradient there, but you have to have a global fluid, and that's what it looks like. And it looks just the same as time goes on and on and on and on. It's like, yeah, sorry.
Number gamma that they found, the PNS paper found, they did, I don't know, universal, can I say universal or it's being inappropriate or I don't know.
Okay, so we don't know about that. I mean, so if you look, Luo and Hou model, as I understand, gives an exponent of 2.5 exactly. They can distinguish. Okay, even I believe I can distinguish the exponent from exactly 2.5. I wouldn't be, if they didn't have that, I wouldn't be so sure. But I certainly see something that looks to be saturated at something less than 2.5. And so you can imagine I spent a whole lot of time trying to think of an argument as to how to, I mean, I've written things in the paper, at least reducing the selection of gamma to the most compact statement I can make, but in the end, I couldn't do anything with it. Obviously it's hard. And I don't have any argument as to why it's, I mean, I'm not sure that.
Yeah.
So the thing is, obviously what you need to do, I mean, you can play with, the models, either mine or theirs, and just see how sensitive or insensitive it is to initial data. And then you could obviously need to do the same thing for boiler flow and see how sensitive.
Yes, that was what I was curious. If you change the initial condition slightly.
The thing is though, that, when you think of that all of, even this is, in a very, very tiny region.
Yeah.
So you don't think that, and as long as it's odd about the mid-plane and certain other things about want it to be maximum, swirl be maximum, the wall probably, and things like that, so other instabilities don't arise. I mean, you want to monotonically increase and swirl. Well, anyway, the easy answer is I don't know.
Yeah, sure.
To reproduce these simulations that I did, require no Newtonian similarity in that, just to say it's not very hard. Anybody can do simulations in a spectral code. See, I can go up to this time and I can read to Luo and Hou to 8 significant digits of precision. So, and this is what I've shown you. They can go to quite a bit later time. It doesn't look like a very big, much bigger number, but the things are blowing up very fast. So it is a big, they've gone down quite a bit further in time. But anyway, you could reproduce these simulations. You could run lots of different cases with my simulations, but I'm not sure how. You have to be very careful about picking out the exponents.
Can you just tell me how do you do the simulation?
It just do some cycle. That's the person sitting next to him.
Spectral, he said.
It just Chevy Chev, or ask Bob Curran.
You don't get any trouble with
He
dissipation?
uses double check.
You don't get any trouble with dissipation?
Not to this time.
Yeah, okay.
Mysterious.
Yeah, that's what I mean, yeah.
I mean, eventually your spectrum is going to saturate the load you have, and then you can have artificial, depending on how you project it, whether you can have dissipation. You can't get away from it. I mean, you're always going to have some just right away. It's going to cascade. Some of it's going to cascade to the highest modes, but you mostly don't. It is all the problems with Euler, but that's why I stopped here. It's good enough for me to get the physics out of the problem. That's where I stopped.
Did you look at the special behavior around the point?
What kind of behavior?
What happens in space? Is there an exponent in space as well? What happens around the singularity?
In a way that is not contained in the figures I've shown.
But he wants to know the vorticity as a function of R or as a function of Z.
Oh.
Yes.
Yeah, lots of the data fields. I mean,
Wouldn't that be an interesting question? I mean, you should have in space as well some behavior towards infinity.
oh yeah. That's right. It's very. Well, but the thing is, it depends on what scale you're looking at. When you blow up to this scale, everything looks as smooth as this. I mean, this is a huge pressure spike.
No, I mean omega.
Yeah, no, I know. Yeah, I know. But what I'm telling you is that everything, when you blow up everything, if I look, just to tell you, I know you, but just to tell you, if you expand out, this looks like a huge pressure spike. So likewise, vorticity on this scale I have the vorticity on this scale. I don't. It doesn't look like much because I have expanded it up to this very little region. But yes, I mean, I'll say. You're asking a reasonable question.
You were talking about the force on the wall. The force on the wall will be infinite or not depending on the spatial behavior.
Yes. Okay, maybe we'll have to. Anyway, yes, I've looked at vorticity and I have the vorticity field. Although the thing is, I guess part of the reason I haven't focused on vorticity in the talk or even having anything very ready is that they focus a lot on vorticity. There's a lot of what vorticity looks like around the singularity. I didn't focus on. This isn't really going to show it. I mean, this vorticity is blowing out. This is on the same scale. This is the azimuthal vorticity. It's not the dominant vorticity, but it is not a vorticity. I don't think I have the other. I should put it. Yes, I have. I mean, I don't have anything to say about this, but it's a good question.
I know that the boundary conditions are different, but maybe your argument would be completely different because we have burgers and this is the drive behind everything. So if you add a tiny viscosity, could you incorporate it at all into your argument, one way or another?
Well, okay, so the thing is, it depends on what you want to do with this viscosity. If you just want to kind of add some I don't know.
I'd like to see how much your argument holds ground with viscosity. Because we know that if you have viscosity, the singularity should not be at the boundary, but then its boundary conditions are different, etc. So I'm trying to see.
Yeah, I don't think I have.
Can you develop? I'm trying to. Can you develop similar arguments in some sense to show me why viscosity can rule out such a singularity at the boundary when you observe? Because under condition burgers with viscosity does not have singularity. So
no, but I mean, the point is the velocity is zero. So, right, so this mechanism of
Okay, look, so one thing you could do is, I agree with that, and that's the basic thing is to, but you could artificially put, you could put a second derivative term in. The thing that would have suppressed the Berger singularity for the Berger singularity. And then ask the question, I don't know if I didn't do that. And then ask the question, does this still blow up? Probably not, surely it would for small enough nu. And so that's saying something about, in other words, that would be saying something about, actually, let me say something about that. The dominant, what I don't like about Berger's, Berger's equation is a nice equation for illustrating basic properties of shocks, but it only involves the longitudinal velocity. And that's actually not the important velocity in this problem. It's the transverse velocity that's the important velocity in this problem. If there's a transverse velocities that come together, they're really important in this problem. They're all important, but that's really key. Anyway, you could put in a little bit of viscosity in here. I would have thought it wouldn't suppress the singularity.
But then singularity should happen on the axisymmetric.
That's what I'm saying.
By quadratic linear.
Yes, that's what I'm saying.
So
See how that's what I'm saying. How does it suppress it?
Yeah.
The argument. I would like to develop arguments similar to yours, show that such an argument will not hold. But actually, maybe Anna's mentioned it correctly that we discussed the boundary condition.
Yeah, the whole, see, the thing is, the whole idea of the model breaks down as soon as you introduce viscosity. You could ask the question about just as, you could, just again, with the Berger shock, you put a little bit of viscosity, you can see how it regularizes that shock. You could do that, play that little game here, but that's not about a real flow because the real flow.
But we discussed.
So, I think it's.
it would be for Javier.
Sorry?
Yes.
Javier.
To appreciate it.
Frictionless boundary condition. Friction or even navigate with friction, I mean, sleep with friction.
But is that, I mean, allowed to do that?
Apparently they do. I'm just saying, if you put sleep with friction, you allow this mechanism of the flow slipping around the boundary, which is your flow. But of course, it's controlled. It's the term, but it produces stresses at the boundary.
You could have boundary conditions which are exactly what you want for your implicit solution. Right? You could have a time dependent exactly mimic.
Yeah, okay, yeah, right.
It's all a bit artificial. Is that allowed?
Okay, so but essentially what we're saying is put viscosity into the interior, but not on the boundaries.
You're missing one boundary condition to do that. I mean, for Euler, you're only imposing the normal component. Okay, so what happened to the tangential? This becomes a second order problem. It's not what posed. It's underdetermined. And
I sort of believe me, I don't have an answer to any of these deep questions which have been asked by a lot of people.
Actually, Anna's suggestion was correct. I mean, you realize, I mean, you have the equation on the boundary, and because the normal component is only zero, so you have the other component is not zero, and therefore you can reduce it. But the minute you have viscosity, the boundary condition, all u equals to zero, and that's it, kaput, you are done.
Yeah.
But still, can you
Exactly.
do something more with that? That's the point. So can you still build an argument?
okay, that's like Dwight.